Assalamualaikum. Assalamualaikum warahmatullahi wabarakatuh. Today we will discuss about design and application of pattern for metal product. Now, metal casting is a very important technique because we can't avoid to develop to fabricate certain part engineering product because there is no other way than fabricated through metal casting. New products are given where how often by automatic cylinder. Now these are the cross-sectional view of a mold. This is the actual product. This is the actual cavity or actual product, the shape of the actual product. But for this product, we have to develop so many accessories in the casting. Now this sand casting comprises of two important elements of the flask. The lower one is the drag, upper one is the comb. It is filled with sand with all these elements. Now, therefore, the steps of the foundry practice is given over here. First of all, we have to make pattern, and then we have to make core. Now, during molding, with the use of this pattern and core, we develop a cavity in the mold as according to the product required. And after having the cavity, developing the cavity in the mold, we uh, melt the metal and we pour it, and then we allow it to solidify, shake them out, and trim off, battle the unwanted material attached to the casting. Now, if this shows the process flow chart of the metal first. Now, first of all, we make mold with the cavity. Now, in the mold, we pour in the molten metal, and in this molten metal, we pour in, we allow the molten metal after pouring is being allowed to cool, and then after cooling, we shake the solids out, and we trim, fatal, unwanted metallic parts attached to the casting, and then we have the finishing operation, and there is the product and the waste. Now, therefore, this gives the after fettling, we have some unwanted uh, metal and some sand is there, and this unwanted metal is again melted and then poured in the mold cavity. Similarly, we can have the metal flow in shake out. This metal is the metal is is creamed off and have the product, while the sand which is taken out is hot, it is cooled, and then it is being processed. After processing, it is mixed with the the new sand, and then they are again being molded, and the cycle continues. But during processing, there are certain losses of the sand because they are unable to be recycled, and therefore we had to add some new sand so that we can have the complete thing. Now, first of all, we need pattern to have the mold. Now it can be a solid piece or solid pattern, or can be a loose split or split pattern, or can be a gated pattern, a masculine pattern, a cope and drag pattern, sweep pattern, skeleton pattern, and master pattern. Now, single piece pattern is that pattern is whole one single piece with all the details in it. And as it is a single piece, we call it a single piece pattern. And the two piece, it is being separated by into two halves so that it can be more efficient for molding, and therefore we call it two piece. Can be more than two pieces, but however it is split. This is split pattern. Now, in cope and drag pattern, one specific part is to the cope and another specific part to the mold, and they are assembled together, and so that we can have the complete cavity. Now, in a match plate pattern, these two halves is that be separated by a match plate. Upper half is that goes in the cope, and the lower half goes in the pattern, and therefore we, as being separated by match plate, we call it a match plate pattern. Easy to. Now another is gated pattern. In this gated pattern, this is actual cavity, actual casting, but to it we attach all the getting system and all the elements which is required for casting, and therefore it is easier. When we are having a gated pattern, it becomes easier for molding. Now, if the pattern is very big, very difficult to transport and molding, and therefore what we do, we make a scraper blade pattern. See, we ram the flask, and then we scrape out by scraping blade pattern, but sweep that out, the extra material by rotating and sweeping that out, and then we assemble it so that we can have a complete assembled sandboxes. Now, if another way to have this patterns of bigger size, they are weighty, and therefore to reduce the weight, what do we do? We are happy only having, we want only the active surfaces. Therefore, we made the skeleton of the pattern, and then we cover the skeleton with the face material so that we can have the surface active surfaces which we need for molding. Now, while designing a pattern, we need a number of allowances so that after solidification, we can have the exact dimension of the pattern of the product. Now, first is the shrinkage allowance, which depend upon the pouring material. Another is the machining allowance. There are certain, if during casting we need certain unwanted material that is to be machined out, so much so that we can have the exact size. Therefore, a proper allowance should be given. That we call that again depends upon pouring material, metal and molding technique. Now another is the dark one, there is the vertical surfaces in the pattern. Now if it is vertical, then very difficult to take that out. This may, while taking out, may erode the vertical surfaces of the mold cavity. Therefore, we need to give certain allowances, and that is up to zero point 0.5 to 1.5 degree. Now, objects like flat plate, dome, U shape, V shape, etc., they after solidification they get distorted, and therefore allowance should be given so that after distortion they come to the original shape and size that we need. That allows the distortion. Now, shrinkage of the metal in mold cavity are the shrinkages are number one is shrinkage during cooling from superheat to solidification temperature, and then from during phase change there is again shrinkage, and also during solidification temperature to room temperature again it shrink, and therefore we need to give proper allowance to the pattern. Basically solid solidification is given to the pattern. Now therefore this is volumetric solidification and contraction of various metals which can be used for our all processes. Now, if you want to design a pattern, suppose this is the length of the pattern, this is the width of the pattern, and there is a cylindrical hole of dimension d, and therefore we need to have we need to have the know the volumetric shrinkage. Say it is y, and linear solid shrinkage is x, and therefore there's a volumetric solid shrinkage, a linear solid shrinkage can be related by this particular equation y is equal to 3x, and hence we can calculate the length of the pattern depending upon, because we will measure the linear dimension, and therefore we will need the linear solid shrinkage allowance to the length similarly to the breast. But you see, there is a hole, and the metal shrink, not hole won't shrink, the metal will shrink, and therefore we need to give an allowance so much so that when it shrinks, the hole will expand. And therefore, we need to reduce the dimension of the cavity of the hole so that after expansion, the size of the hole becomes the size that we need in the casting. And therefore, it is to be reduced by that particular amount. Now these are the pattern material, maybe wood of different type depending on requirement, maybe metal, aluminum, brass, white and cast iron, maybe quick setting compounds, gypsum, etc. Can be wax or can be plastic also. There are different material depending upon our requirement we can use a metal material. Now this pattern has different surfaces. Now, those surfaces where we left only for cast is being painted red or orange. This shows that this pattern will be directly contact to the mold surface, and yellow to the surface is to be machined, so that accordingly we can take care of it. Black on the is to be painted on machine opening like the core print. Now yellow stripe or on black on cold print where to be machining operations, and green on seed to be melted so that we can recognize the green one. Now there are certain locations in the pattern which are weak, they need strengthening, and that is to be painted with clear varnish with black strip, so that we can get proper reinforcement and proper handling, and that and precaution while handling should be taken to those locations, and therefore they are being color coded accordingly. Now these are the few tools and equipment for pattern making: saw making machine for wood, lathe machine, planer machine, sandpaper machine, drill machine, file, chisels, tri-squares, divider, calipers, bevel protector, hammer, mallet, uh, pincers, bench vise, etc. These are the few tools which are generally used for making patterns. Now, with the development of technology, pattern making has also been developed, and therefore now we can adopt different developed techniques like additive manufacturing, rapid prototyping. In that, say 3D printing and selective laser sintering, stereolithography, laminated object manufacturing, fuse deposition, laser engineering, head shaping. These are the new developed techniques. They are costly, but however, we can use them to develop patterns, and those patterns can be used to for making molds and the castings. Now, the one of the important element in molding is that we call core. If some cavity is required, we need a core, and therefore this core is nothing but a device or element to develop internal cavity in the cast, whether it is a hole or maybe a small cavity. Now, therefore, we need to where we can't have the green sand can't be incorporated, can't be strengthened, and there is chance to fall down in the cavity, and therefore we assemble a core in that. Now this is a figure where you see this is the main casting. This is the main casting. Now this casting needs a hole, and therefore a core is being provided over here. This core, this is yellow one is the core. This core is provided over here so that a hole can be developed in the product itself. And therefore, but suppose this is just a cylindrical job with two flanges, and it is the hollow one, hollow cylindrical job with the side view and view and the front view. Now we need to provide core print, because to make a hole we need a core. Now this core can only be assembled in the cavity when there is a space holding the core. Now that space can be provided by providing a core print in the core itself. Now, therefore, it is to be properly designed so that this core print should be strong enough to stand to hold the core and withstand the pressure and the forces on the core by the molten metal surrounding the core. Now, therefore, the core making is done. Core is made by in a by using core box, and this is the core box, and cavity is there in which the core material is packed, and they are being hardened, and therefore and can be used as in. And this is a typical what do you call core box, a core box. Now the core boxes are made are the molds. Core boxes are basically the molds that of wood or plastic or metal. Now sand mixed with binder is packed into the core. The core is sand mixed. You see, we also call the core sand. They are with binders, of course, is packed in the core box, and then they are removed and they are baked so that they become hard. And sometimes these cores are also coated with core wash if a high temperature resistance is needed. That can often contain graphite to give a high temperature resistance. Now, if some core is also, as I've told you, core is also made of sand, and therefore, when metal flows, it may cause to develop vapor in the core, and therefore, there should be proper venting with the help of tube, so that these vapors may be taken out and may not get mixed in the molten matter and provide certain defect. Now, core, if it is weak, they can be reinforced with wire, sometimes a rod, metallic rod, so that it can be strong enough while to resist the forces and also during transportation. Now, let us see what are the forces acting on the core. As shown in the previous slide, you see the band force surrounding the core will try to lift the core or misalign the core, and therefore this band force can be given by Fb, where V is the volume of the core, and this rho m and rho c are the weight density of the molten metal and rho density of the core material, and this will give the total amount of band force acting on the core. Now, this forces acting on the core can also be empirically calculated by this particular equation. Now, where A is the area of the core print, A is the area of the core print, see, cross-sectional area of the core print. Now, this is the force acting on the core. Let us see what are the forces acting on the mold wall due to this band force which is acting on the core. Now, band force acting on the of the molten metal will act on the core, and this force will be balanced by the force acting on the wall. That should conflict, and therefore let us see what are the forces which will withstand this force, and therefore this Fc is the forces acting on the wall of the mold cavity due to the core, and that can be given by the diameter of the core pin and length of the core pin, where Ss is the compressive strength of the core pin, and therefore we can understand that this much amount of forces is acting, which is acting on the mold wall, and therefore the core pin should be strong enough so that it can withstand the mold cavity. Otherwise, it will shear away the mold wall. Now, this gives a few liquid densities of few materials and molding sand. Therefore, we can calculate. Now, chaplet. Now we know the core is being assembled in the molding sand with the help of core print. Core print gives a cavity, and therefore, but sometimes in some cases it is very difficult to have the core print of which can withstand sufficient forces as we have studied now. Now, therefore, the metallic support is provided to the core that we call chaplets. Now, it is generally used for large and odd shaped cores, and cores which can be supported can't be supported by their own core print, and therefore we need to supply these chaplets. Now they are placed in the mold between the core and the fork so that they can withstand the forces. Now this is like an example. This figure shows. Now this is a chaplet, metallic chaplet. Now this is the core. Now this is our hang core, cantilever type. Now therefore there should be need a sufficient support so that the molten metal which is flowing in the cavity may not misalign the core. The core. Okay, and therefore now generally these chaplets are made of the same material that of the molten metal. Now during flying, it also get melted and get dissolved in it, and get lost in the get dissolved in the molten metal itself. However, therefore, you see, we can have this is the mechanism. This is how we can hold the core with the help of chaplets. Now there are different types of chaplets depending on the requirement we can use. Now, there are different types of cores. According to the composition, they can be green sand core made of green sand, dry sand core, oil sand core, loam sand core, metal core, or according to the position, how they are being positioned in the cavity itself. Can be horizontal, can be vertical, can be balanced one, or power core, or hanging core, or wing core, depending our requirement we are having. And therefore, depending upon this, we are having also different types of core boxes. Can be half core box, can be dome core box, can be split core box, can be speckle core box, or can be core box, core box. Now, half core box is that core box. It is a cavity over there. You see, it makes half of the core. Now, suppose two pieces of it will make a complete core. We have to assemble these cores together so that we can have the complete one. Now, there is a dumb core box also, you see, which is having a complete core, which develops a complete core, and can be split type. We split the core box as two different parts, and we assemble them together, pack the cavity with core sand, and after packing, we separate them, take that out, bake them, ready for the cores are so that ready for assembly. Now, if in one core box you are having a number of cavities so that we can develop a number of cores, then that type of core box is known as GAN core box. But if there is a typical type of core, an irregular shape of core, then generally we obtain by striking of the core. First of all, we fill the core box and strike off the excess core sand by a piece of wood. The piece of wood is known as a Strickle board. Now, the Strickle board has the same contour as that of the core, so that we can have the contour of the core should be same as that of the core we need. Now this is the core box in which the sand is being filled, and by Strickle one, the Strickle board, the extra material, extra sand is being stacked off, and then they are allowed to have the shape. They are taken out, they are baked, and now ready for assembly in the cavity, mold cavity. Now, therefore, now let us see what are the forces acting on the flask. What happens that the molten metal is having a buoyancy force on the core. Not only this, the whole cavity will have a buoyant force on the cope itself. Therefore, we need to see what are the forces, what are the buoyant forces which is acting on the core. Now, therefore, this can be equal to Fm is the forces buoyant force by the molten metal, or depends upon the area of the projected area of the casting. Now, this rho is the weight density of the metal, H is the head of the metal and C is the height of the cavity, and therefore this gives the force acting acting on the upper half of the flask, that is the cope of the flask, cope portion of the flask. Now, therefore, if this buoyant force is more, then we have to apply force, weight on the cope. If it is less, well and good. Otherwise, what will happen if the buoyant force is more? It will lift the cope and the molten metal will flow out. And therefore, we should have a proper clamping or apply proper weight on the cope so that it remains on the same position. Thank you for listening.